Robin currently works at the Munich Institute of Robotics, Machine Intelligence at TUM. She studied sports engineering and mechanical engineering at Chemnitz University of Technology with research visits at Nagoya University. And she is currently focusing on developing concepts and metrics for safety in physical human-robot interaction and tactile robot skills in industrial applications. So Robin, you can start sharing.
Perfect. Thank you very much, Rudy. So I'll now share my screen here. Thank you. I think you can all see my screen nicely, or I hope.
Yes.
So thanks very much first to the organizers for the invitation. It was quite a spontaneous one. We have been working on this tactile interaction for quite a while now, for like around 3 years, and how to benchmark it. And I'm trying to give today an overview and a wrap up of the work we have been doing the last 2 to 3 years. Yeah, and I'm looking forward to discussions afterwards. Here we go. Yeah, we are the MIRMI Institute, the Munich Institute for Robotics and Machine Intelligence, part of the TU Munich. And here we have the Robot Performance and Safety Lab, which I am currently managing. My senior scientist is Dr. Saeed Abdulshah, and we are all part of the chair of Professor Haddadin. And in our lab, we have created a set of test devices and everything. And finally, one of the heart or the core points of this lab is to look at different robot technologies. And here we have established a little robot zoo where we can test and work with like different type of collaborative robots and also do education with these robots. Well, today we are talking about the research. In our lab, we have 2 main focus points. One is robot tactile performance, and the other one is human safety. And today we want to focus about the tactile performance, actually. So why tactile? Why tactile robots? What is it about? Why do we even call them tactile, and what do we think is useful? In traditional, actually, position-based automation, we have one key disadvantage currently, which is especially if we want to do assembly tasks or have tight tolerances, we need to have very precise positioning, which requires a huge setup around the robot and around just having the manufacturing or the workpiece. Now, if we look, for example, at gear assembly tasks, where we have very tight tolerances, such that the bearings actually fit, we can see that if a human is assembling this kind of assembly groups, it needs a very small space, actually, and is capable of doing this quite efficiently and fast. While if we want to automate this whole procedure, we need to subdivide into smaller tasks. We need to have very precise positioning, and we end up with very big automation pipelines, like one is depicted here. But what is the key point of the factory of the future that we imagine that we want to achieve at some point in time? Well, we all talk about here is production as a service. So we want to not have big automized cells where we have a lot of opportunities for actually big positioning and the whole equipment around this positioning problem. But instead, we want to have single agents that can interact with each other, that can be shifted and moved to perform different tasks. And the key point is that we cannot necessarily verify the exact positioning for objects in this case. So the idea and the advantage of the tactile robot here now comes into place. When I'm talking about a tactile robot, I am here referring to a manipulator arm that is capable of sensing actually contact. Now, this is one of our demonstrators that we actually set up in a museum here in Munich. And what it's doing, it's just supposed to follow the contour of this shaft that we have created there. And you can see, you can change the contour of the shaft, you can change the order of this mount hills. You can even put your hand under it and it will still successfully perform the task of applying a very low force and keeping the contact to the shaft. And as you could see, I put my hand underneath this robot and I was fine. I just got a bit dirty because it has some dust, but otherwise nothing happened. So the key advantages of this tactility that we see is once the adaptiveness to different tasks by understanding what is actually contact and also potentially being able to differentiate between contacts. The human safety, because we can verify that contact forces are not being exceeded, and also the efficiency by teaching the hand guiding operations more flexible and feasible. So state of the art right now, when we're talking about this kind of collaborative or tactile robots, as I said, alone in our lab, we have this 7 different type of robots currently. And there is, I think, currently 170, I've read lately, different collaborative robots of different technology out there. All of them use different sensors, all of them use different sensing strategies even. So some might use force torque sensing directly, others use torque sensors and use the robot model to estimate forces. One robot might only use the motor current for actually detecting contact. And then based on the whole mechanical structure, they are all very, very different. So usually, if I try to introduce my topic, I have the people at the lab and I can show and let them move the robots directly. But here, just taking the robots and hand guiding the robots around their workspace, you can already see and feel the differences. I hope you can understand and see also from these pictures now, these videos that I tried to capture. In the one hand, with the one system, it might be very easy to move it around and you can just use one hand and guide it anywhere you want. While other systems have a bigger friction in their joints and it's actually quite hard to move them from point to point. So this is this difference that you can here now already see, well, qualitatively, but the question is now, how can we get away from this qualitative evaluation? How can we actually quantify what this system's tactile performance is? And here we have taken, so we were a team of, I think, 7 people in the beginning, discussing about different possibilities, how to actually classify and look at the different metrics, what is required. And so finally, we agreed on having the force sensing, force control, the human safety, and the usability as the 4 key groups for this tactile robot performance. For the force sensing, well, I'm keeping it quite simple here just to not make it too long. Obviously, the absolute accuracy of the sensing is really important. The repeatability, how well can I actually repeat the measurements with this robot? The resolution, so how fine is the differentiation between different forces, and the drift of the sensing over time is here the key features that we look at. The setup that we currently use here is very, very simple. We just have a robot and we attach a mass of a known weight to this robot. And then we let the robot give the forces that it's measuring, and we compare to what actually we have attached to this robot end effector. Yeah, the force control is also, I think it's quite natural, understandable. We also look at the absolute accuracy here. So if I ask the robot to apply a certain force, what force is actually felt by the counterpart? Also here we look at the repeatability. We always measure 30 times, by the way. The resolution, how fine can I distinguish between applying different forces, the overshoot, settling times, and the controller bandwidths. For that, we also use a setup like this one here. We use different testing positions and have a sensor attached to a stable surface. And here on top of the sensor, we can actually place different covers with different stiffness. Usually for our benchmarking experiments, we use a PE cover, which has quite a high stiffness. And then we use a ball, a sphere, that we attach to the robot end effector in order to contact the sensor and see which forces actually occur. Next, I'll show the usability part. This is a bit more tricky because here we are talking mainly about the kinesthetic guidance performance. With this kinesthetic guidance performance, it is not as intuitive what you would have to measure. So we lately did a paper summarizing the work that we've done here. So first we had to investigate what is actually the key features that are part of this kinesthetic guidance performance. So what we tried was to understand what is happening during this guiding, and we came up, or we investigated and saw that there is like 3 main phases that you can distinguish, which is once if you take the robot and start to move it, you will first have to have this little breakout force that you have to overcome. And this force is very different depending on the friction of the different robots. Then you have an acceleration phase where typically a robot manipulator has more than one joint. So all of the other joints also start to break loose and you're starting to accelerate the whole system. There you see actually quite high fluctuations in the force that you need to apply. And if you manage to get into a steady motion where you have a stable velocity, you see that the deviation of the force becomes smoother. In order to quantify these, we have looked at this minimum motion force, this breakout force. We developed an own test stand for this, which can actually move into 3 axes, X, Y, and Z. And we can investigate in any direction and any kind of motion pattern, which forces is required to move the robot. And for the minimum motion force now, we looked at the force that we can see when first we can say there was a motion really detected also. And this force we then refer to as the metric. Secondly, for the motion steadiness during the acceleration, we notice in the force profile this high deviations. And at the same time, we can actually, just by experience, feel that the robot is wiggling quite a lot. So it is trying to escape somehow the force that you're actually trying to apply. And for this metric, we wanted to show what happens now if I do a constant acceleration. For that, we use a weight. We attach this weight to the end effector over a pulley and a rope, so to stabilize the force in one direction. And we trace the displacement of the end effector using a retro reflector and the laser tracker with it. And then we record these trajectories that we can actually see and compare it to which would have been the ideal path that the robot should have followed if it was really just following along the force that was applied in the beginning. And here we can see, like for different robots, there is different settings possible. For example, restricting the motion in X, Y, or Z axis, while it's also possible to just use a joint motion, and then freely every joint can move. And obviously, as we can also see here in this graphic, there's, with this free guiding motion, the robot deviates a lot from the theoretical path. And with restricting the robot in its Cartesian motion behavior, it stays a bit closer to the ideal path that we would want to achieve. The guiding force and guiding force deviation is the metric that we use actually for the stable motion. So once the motion profile or the velocity has actually stabilized, we look at the forces that occur here, and we take the medium at the standard deviation of it. Also, once again, using the same setup as in the first metric, which we can see here. So for our general investigation, we always used different velocities and compared them towards each other. But now for the performance benchmarking, we've seen that the velocity of 250 millimeter per second is actually the most interesting one, as it's also referred to as the kind of hand guiding velocity that is allowed in human-robot interaction. And additionally, to evaluate the actual usability in the sense of ergonomics, we also introduced the metrics of the guiding energy, which is derived from the entire phase of the guiding. Exactly. And lastly, in our metrics set, we have the human safety. As you have all answered already earlier, the human safety actually plays a big role for tactility and other way around, actually. The two most important metrics here are the contact sensitivity and the constraint collision force that occurs. For that, we have established one pendulum setup where we can attach a lot of different weights, and we collide with the robot with these different weights, and we have also different damping covers that we can use to model different collision scenarios. And we observe whether the robot was able to detect this contact or whether it was not able to detect this contact. And in case of the constraint collision force safety, we refer to the ISO TS 15066, which suggests to have some biofidelic testing devices in order to evaluate forces that are comparable, that would occur in a comparable way when we have actually a collision with a human body part. And the results then look like this here. So for the contact sensitivity, we always looked at whether there was a collision that was successfully detected, which is in this case the white patterns here, or if it was not successfully detected, what would be the blacks here. And then we also looked at the braking time and the braking distance. But currently, we are overworking this a bit. That's why I'm not focusing on this too much right now. The constraint collision force safety we then obtained by looking at the different contact conditions, so comparing to the different body parts suggested by the ISO TS, and which forces would actually occur at a collision with the robot with a certain velocity. And then we compare it to how many % of these cases would have been considered safe following the norm. So for our results currently, I am just giving a short excerpt because we have obtained now a lot of results, and if you're curious, please take a look at the papers. So just for the general understandings, we can see with different systems, especially for the force sensing strategy, we can already see that there is massive differences. So if we just look at the accuracy of the force sensing, while one robot might be able to detect the forces by 0.3 Newton accuracy, the other robots might not be able to do this. They are at accuracies within 5 to 6 Newton here rather. And also the repeatability of this force sensing varies a lot. The controller strategies, here we can see like really the huge differences between using a position control or using torque control, because if we have position control, even if we are capable of sensing a contact, we still have a delay in actually trying to control this contact, because we need to calculate back on what is actually the position I need in order to create a certain torque or force. In this case, also, we know from the previous slides here that the sensing is not very good. The sensing, not very good sensing, and the slow reaction possibilities to a force then lead in this case even to that this robot is not capable of really applying a stable force. It is always synodially wiggling around the actual desired force, while other robots that kind of use here torque control measurements, they show a certain overshoot at the first contact to the sensor that we have. Then there's a settling time that we can give, and after that there is quite a stable force that is very close to the desired forces actually occurring. For the kinesthetic guidance, we can also see this very big differences, also considering different settings and motion directions. Here we've done a very extensive study with most of our robots that we currently have at the lab. And yeah, interestingly, what I can say maybe already about our current ongoing work is that we can see even like that there is a statistical significance between the motion forces and the guiding forces and the robot safety and tactile performance in total, which is quite interesting. So this kind of means that if you go on a fair or if you go to a robot and just take it and hand guide it, you can already do some quite nice predictions just for yourself about how tactile and how safe this robot will actually be. Yeah, and the collision safety also here, we can see the large differences, especially the tactile, like this tactile interaction or the tactile performance of the robot influences this contact sensitivity. Obviously, the better and the earlier I can feel the contact and actually quantify the contact correctly, the earlier I can also react to it. And if my sensor is capable of repeatedly measuring the same values, then I can also achieve a very high reliability in this contact sensitivity. And this reliability or not reliability, one can see actually when looking at the at how even these white spots are distributed. For example, here in this case of this robot, we can see that even though at a lower velocity at the same mass, it has already stopped and shown really at least this measurement was a reliable stopping behavior at a certain setting. At the next setting where it is actually faster, but it's still the same velocity, where you would expect that the energy increased and such that the robot should definitely be able to detect this contact. It might not. In this case, it didn't. detect this contact, which is closely related to the reliability of the sensing. So what is the conclusion for the state of the art of robotics that we can currently draw from all our existing investigations? So what we see very, very precisely is that we have this strong dependence of human safety on this tactility metrics and the collaborative robot efficiency. So how fast can I have a robot actually move in order not to have any injury potential is also linked to this tactility performance. And lastly, also the ease of integration. So what is the ergonomic behavior of this hand guiding is also closely related to tactility. Yeah, for an outlook, so we are currently trying to derive a big database on all our present and new upcoming collaborative robots that we have at the lab. So we are increasing our robot zoo, not only for this, but also for teaching purposes. We are then, based on that, trying to understand the fundamental differences that actually we can observe. What is the reasons for that? Like, is it about the torque control? Is it about position control? Which sensing strategies seem to be the most promising ones? And we also want to relate this to the task requirements. So looking at industrial tasks, what is the sensing performance that I actually require? And lastly, we are now working on integrating this knowledge to the industrial safety reality. We're trying to go for the standardization committees and trying to approach them and show our measurement methods and make them understand that this is actually a very important part of robotics. Okay, this actually brings me also to the end of my talk for today. I hope I could tell you a little bit about our work and why we think it is important. And now I'm looking forward to any questions and discussion.
Thanks, Robin, for the wonderful talk. And so if anyone has any questions, feel free to start. Maybe I can just start with one quick question. What do you think is like the current challenges in safety or using this tactile information, and you want to bring these robots more in industrial human-robot collaborative scenarios or to the service industry? So what are the main things that one needs to look at in terms of these two aspects?
So one of the basic challenges is really the standardization that we currently have. To bring collaborative robots to industrial reality is very difficult at this stage because the safety requirements are, on the one hand, very restrictive, and this whole metric, this whole standards based on kind of the old days where there was no real torque control and there was no tactility in robotics. So it doesn't allow the space currently to actually implement this stuff in a safety certified manner, such that all of the companies always tell you, yeah, it's nice that you have this collision reactions, for example, that they can in time detect a contact because they are sensitive enough. They have this tactile behavior that they can fulfill the detection possibilities and they can then react, but it's not conformed to the safety performance levels that is considered, because it is even a technological challenge to fulfill this performance criteria for the safety performance levels. And that is definitely challenge number one.
All right, thanks. Someone else? You can also write in the chat if you want to ask something. Okay. Seems like everyone got what you want to say. And
It seems like I overwhelmed everyone.
No,
Maybe too much
No.
information squeezed in too less time.
no, but if you had to restart from scratch your research now, like with respect to what you have done, what would you do differently? And like, because I think like when we first start to research or the PhD, we have a certain idea of the things we would like to explore. But then our research kind of changed throughout. And now that you are at this point, you already investigated the topic for quite a while, you have this very nice presentation where we see kind of fil rouge of the topics and the safety and the touch and everything. First, how did you get to this line? And what were the steps that you encountered that you didn't talk about during the presentation, but that led you to this point? And second, what would you do differently?
Okay, so it's nice that you call it a line, because for me, it was definitely not a line. It was more wiggling around and trying to explore different topics. I have actually started off in a very, very different direction. So safety in human-robot interaction was always clear to me because that was kind of like my big interest. But then when I started at our institute, I started also investigating more in the direction of psychological aspects of this safety. I wouldn't say I would do that differently because I still think this is very, very interesting. And I am now at least trying to supervise the next upcoming topics in this field as well. So no, I would not change that. But in the beginning, I have to say that there was also not a lot. So we founded this lab 2020. I started 2019. And it was a lot of work building up and building concepts and really building up the devices and everything. I didn't listen a lot to my supervisor back then, to be honest. It would have been more stringent if I had listened a bit more. But on the other hand, I did a good journey learning during that time. So I don't think I would change that much, to be honest. I think this is research, that you don't have a line, you have a circling around some topic, and sometimes you go a bit off, and then you can find your way back. At least for me.
If you had to list some of those topics, we have another question, but just quickly, if you have to list one of those topics that you like explored, but then decided to not explore, can you mention some of them? Like some of the things that you started seeing and then you said, no, this is not the direction I want to follow and I want to pursue, or maybe like some experiment that you tried to set up, but then you said, this is not actually testing my hypothesis, or this is not actually the good design, or this is not actually what it should be.
So in this field of the performance benchmarking, we have tried around a lot, also like with torque. So everything we did right now or showed right now is all force based, but there's not only force, right? There's also torques, which you would need to consider. And we tried a lot with this torque measurement and how to really get good devices here. And yeah, the problem is, especially with the torque, you need extremely high precision in the manufactured devices that you build. Otherwise, you will always have problems with the just from your measurement setup created on your measurement. And that I kind of ignored in the beginning, so I just had it roughly manufactured, and yeah, then always ended up with results that caused a lot of discussions and were not very satisfying. So yeah, you learn from experience.
Maybe Iris.
Thanks, Robin.
Hi, my question would be, as far as I understand, most of your research is based on proprioception, and how, like, that is actually also fitting well to what you just said. How can the results that you have now be maybe also used to equip robots with a better, like, sense of touch in surface means, like skins or tactile sensors for end effectors? How would that help in your opinion, and how would they need to be designed to increase safety?
Mm-hmm. So technically, using our metrics, you can test any device. It doesn't necessarily matter. You can also not have a manipulator. You can use anything else. But what we've seen, at least for the robots currently, is that especially for the control and for the sensing, this performance, it is very, very important to have a proper manipulator model. So the modeling behind this manipulator in order to perform good sensing is really, really important. As soon as you have the measurement over joint torques or motor currents or stuff like that. If you attach, obviously, a force torque sensor in front of the robot or on the end effector, you will definitely get better sensing results, but it might cause trouble in your control depending on how you've integrated it. So it's really important that the sensor that you use is properly integrated into your controller, that it has a very low response time. So the whole communication needs to be really, really fast. So these solutions that currently are being used quite a lot, implementing having a usual lightweight robot and just putting a sensor in front is nice. It will also do very good sensing results as long as the sensor is good. But the problem is to integrate it into the controller, you have to have very fast communication lines. And here, what I see currently is also the problem that if you control based on positions, you always have to calculate back from the position that you want with the force to the motor torque, which is then translated into the position again, and this is all slowing down the whole communication channel. So this is currently, at least what I see for our robots, that for these manipulators themselves, you need to consider the response to a certain sensing method. If you use torques and motor torques or whatever, you have to have an appropriate robot model. And if you want to extend, like with skins or whatever, you need to make sure that the communication line is fast enough for good responses.
In your experience, what is fast enough?
As you mean the time that it takes to?
Yeah, the latency or the frame rate. Mm-hmm.
So currently the best robots that we have work at 100 Hz, 1000 Hz, so 1 kHz communication frame rate. This is the best we have. Mm-hmm. It works quite well. I don't know if you gain more if you would try to go faster. I don't think so. but I didn't do a huge investigation on that. So I can just speak from what we have and see with the robots currently. So you're working in the field of tactile skins and
yeah, tactile sensors, like more large scale sensors. That's what I'm working on exactly.
nice, cool. So from your experience, what is the sensors you're investigating, and what is the most promising in your opinion currently?
Well, I'm just starting out putting the sensors that we have developed on robots to see what they can help and how they can be integrated.
Nice.
They're running a lot slower than 1,000 hertz, though. We're currently at 60.
60. Okay, that might actually be a bit slow, but you will see. Maybe there's also good solutions to that.
Yeah. Let's see. Yeah, thank you for the nice talk. It was very interesting.
You're welcome.
Maybe just a quick question. I've seen you like staying up long nights here and doing user studies. How much do you think is these human factors important in these aspects and bringing robots more?
Well, human factors are generally in our field overlooked quite a lot. As humans are not easy to understand, but it is, the human is the user. So whatever technology you develop it for a human. Otherwise, if it's not being accepted, if it's not being used, because it's not human friendly in some way, it is not useful. So what we investigated back then was the reaction to different approaching velocities, trying to see what is still accepted as like an approaching velocity around the human, especially in the context of elderly care, which is where currently or one of the major fields that we are also looking at our institute, where robotics can actually give a huge benefit in really taking care of the elderly at home, for example. And if you want the elderly persons to use your robotic devices, they don't only have to be efficient, but they also have to have, let's put it stupid, but they have to have manners. They have to behave in a way that is expected and accepted to the human. And this is also something that I was lacking a lot in the whole safety aspect and the safety certification stuff. Even there is now norms coming up for mobile manipulators in healthcare and stuff like that. They still don't consider anything human factors related. And this is what stroked me a bit. And so we tried to do we did some studies on that topic, and they are also published. You can read about it if you want to. And I see a huge potential also in this field. For myself and also for my PhD, I had at one point to decide which direction I actually want to go. And as I'm managing this lab and this, I've grown to my lab. Let's put it that way. There's a lot of heart in there. It was not possible for me to say I'm going away from the mechanical part and I'm leaving this lab kind of behind. So I decided to go for the more technological side of my research and pause the human factors, at least for a while. I'm not leaving it totally, but I paused it.
Thanks. So if there are no more questions, I think we can start wrapping it up. And just for quick info for the next talk, we'll be having Yahav, and he will be talking about motion planning and specifically introducing the Jacobi library, which they developed at Jacobi Robotics. And feel free to spread the word around. And yeah, see you on 30th November then. Thanks for joining. Hope everyone